Okay, we're going to be going over 3H, which is going to be the gravitational force. So the gravitational force, we've actually talked about it before, but not in a ton of detail. So we're actually going to be getting a little bit more into it this time. So the force of gravity, it pulls all objects with mass towards each other. So we've talked about the force of gravity between, planets or objects in the Earth or another planet, but really gravity attracts everything to everything else. So again, could be any object. As long as it has mass, there's going to be a force that's between them. Near the weight of a planet, as if you've seen before, we call this force of gravity, we call it weight. So again, remember that on a planet, we call that force of gravity. Near the surface, we call that weight. Again, from Newton's third law, all objects with mass are going to exert this gravitational force on each other. And this gravitational force is attractive, meaning that it pulls everything towards other stuff, and it's of the same magnitude. So let's give an example. You, right now, you're a stick figure, you're on, I don't know, either a desktop or a mobile device. Technically, there's a force of gravity between you and that computer. And again, the force of gravity is going the opposite way for each one of you, but it's acting on both of you, and it's going to have the same force. Let's say, or it's going to have the same size of that force. Let's say it's 10 newtons. So again, that's the third law. And again, the force of gravity acts on all objects with mass. So now let's get into a little bit more of the math behind the the law of gravitation. So this is the mathematical representation of the force of gravity. Again, this is a little more detailed than we've looked at before. So again, this lets you calculate how big that force of gravity is between two objects. So two masses, M1 and M2, those are the masses of the two objects. They may or may not be the same size. They could be different sizes. I'll draw them different just for this example. The next thing is you'll notice the d squared term under here. So d is the distance from the center of the two objects. So not the distance between the surface of the two objects, the distance between the center of them is d. So from the center of this object to the center of this other object, that's the distance that's looked at in the equation. Then this last term, g, this is the gravitational constant between the two. It has a value of 6.67 times 10 to the negative 11th. And it has this weird units. It has Newton meters squared over kilograms squared. It's a little bit strange units. But that's the last thing. Again, this is a constant. This is always the same. So that's really the gist of the notes here. So again, gravitational force, it's attractive. It pulls all objects with mass towards each other. Near a surface of a planet, we're going to call it weight. We call the force of gravity weight. There's a mathematical way of representing it, and we're going to use this for calculations. And then it has really the only new quantity is the constant. I think we've talked about distance before. We've talked about mass before. But the gravitational constant is kind of a little bit of a new thing. Okay, it's probably best to see this as an example. So we'll get into the example. So again, before you copy down the solution, make sure that you attempt it first. So take a second, pause the video, attempt it. You'll be checking in on Foursquare or something else. Make sure you're doing it. Okay, I want to go through how to solve this. So here's the problem. We have an apple. So we have a Honeycrisp apple, 82 grams. and it is a known distance from the center of the Earth. If the apple weighs 8 newtons, what is the mass of the Earth? So we're ultimately looking for what is the mass of the Earth. So how could we find that? Well, let's write out what we know here. So again, we have an apple and it's being drawn towards the Earth. So really, when we think about that, there's really a force of gravity between them. And that might be helpful if we think about that law and think about what we know and how we could figure out that mass of the Earth. So let's write out the law of gravitation. Again, big G is equal to m1 times m2 over d squared. So again, we actually know a lot of this, and this will let us find what the mass is, or the mass of the Earth. So we actually know G, big G, it's 6.67 times 10 to the negative 11th kilograms times meters squared over, should be newtons meters squared over kilograms squared. The mass is 82 grams, which we should convert that technically to kilograms. So it should be 0.082 kilograms because we're moving the decimal over 3 places. The other way. We'd be moving it 3 places to the left because, again, there's lots of grams in a kilogram. We know what the distance is between the Earth and the apple. It actually tells us kind of explicitly that we know what that distance is. So we know that distance is going to be 6.40 times 10 to the 6 meters. And again, it's to the center of the Earth. If it was the distance to the surface of Earth, it'd be really, really tiny. But again, it's the distance to the center of the Earth. And we actually know the weight. Again, that's the force, because we're assuming the apple's pretty close to the surface of the Earth. The weight and the force of gravity in this case are really the same thing. So we actually know what that force of gravity is. 0.8 newtons. And again, we're really looking for the mass of the second object, which is the Earth. So now if we look at this, we actually know everything. We know constant, we know the mass, we know the distance between the two, we know the force of gravity. So we have enough information to find the second mass, which is the mass of the Earth. So we really, at this point, just have to be careful plugging everything in. So we're going to plug in 0.8 newtons is equal to 6.67 times 10 to the negative 11th times the mass 0.082 kilograms times m2 divided by the distance squared, so 6.40 times 10 to the 6 meters squared. And if we do that out, first thing would probably be to multiply this denominator by 0.8. So multiply 0.8 by 6.40 times 10 to the 6. We're going to get out 3.28 times 10 to the 13th. 13 is equal to 6.67 times 10 to the negative 11th. 0.082 times m2. So again, what I did was I'm multiplying the denominator by the left side of the equation. So I'm getting, the equation's getting a little simpler here. And then this last line here, we really just have to divide both sides by the numbers that are on the right. So we're going to divide 3.28 times 10 to the 13th by these two numbers. And when we do that out, we'll solve for the mass 2, which is the mass of the Earth. And it's 6.00 times 10 to the 24th kilograms, which is actually pretty close to what the actual mass of the Earth is. So we're not that far off. So that was a problem. That was a pretty good example of what you're going to see when it comes to looking at the gravitational force. So again, make sure you have your problem copied down, make sure you have your notes annotated, and that's it for now.